Okay, today I'm going to show a simple example of a 2D simulation of an incompressible inviscid flow over an airfoil. So let's create a new simulation. What we're first going to need to do is to create the geometry. For a 2D simulation or for an airfoil, generally we want to provide a list of coordinates, and we want that to be as detailed as, well, reasonably detailed. The way this is done is in a series of x, y, z coordinates. It's important that we have the z, even though you can move it up and down, it needs to be at 0 for a 2D simulation. The reason is that in StarCCM, to create a 2D simulation, you actually first have to make a 3D volume, and then when it converts it to 2D, it takes everything on the z equals 0 plane. So we want this airfoil to be right on z equals 0. How did I get these coordinates? Well, here I'm doing a NACA 2412 airfoil. This airfoil has a mathematical definition based on some polynomials. It's very simple to program that up, but in this case, if you wanted to, there's an website that makes this pretty easy, Airfoil Tools. So here I put in the 2412 airfoil. I wanted the maximum number of points to get the best definition of the geometry that I can. And then I put in cosine spacing, which means it's linear in cosine space rather than in linear space, so that it clusters airfoils more towards the leading and trailing edge, which is important because that's where the geometry changes more rapidly. And in this case, I'm going to close the trailing edge. The actual definition for the NACA airfoil has a blunt trailing edge, but to make things simpler here, I don't want to worry about the base drag and getting that just right, so I'm going to make it a sharp trailing edge. Okay, and then these coordinates are just copied and pasted in that file, and I added a 0. Apologies if it's a little hard to hear, I'm getting over a cold. Okay, so the first step in CFD is to create the geometry. You can import a CAD model, or you can build one using the CAD tools that are in StarCCM. In our case, our geometry is quite simple, so we're just going to build it here in StarCCM. We're going to start by importing that 3D curve that was created as a CSV file. And we have a choice to do a spline or a polyline. In our case, since the airfoil has a sharp trailing edge, the spline would actually work quite well. That would actually give us probably the best definition of the geometry. The polyline is just linear, sort of a linear fit between points. I'm actually going to do a polyline in this case because I want to be able to grab, as we'll see later, the leading and trailing edge lines and label them. That'll help me with my mesh creation. So in this case, I'm going to do a polyline. If you had a blunt trailing edge, the spline is not necessarily a good option because it will try to smooth out that blunt part, which is probably not what you want. Just a note on geometry, you want to make sure you have sufficient resolution. In other words, it needs to be smoother than your mesh. So as an extreme example, let's just say I only had 20 points around this airfoil, like 10 on the upper and 10 on the lower surface. You would be able to see this faceted nature to this airfoil. That means that no matter how good my mesh is, how refined I make it, I'm really capturing a geometry that's very different from the actual airfoil geometry. And so whatever you're simulating, you got to make sure that you have sufficient resolution in your geometry model so that it's a finer resolution than the finest mesh resolution that you want. Okay, so this one looks pretty good. I'm going to extrude it. I need to create a 3D representation now. It doesn't really matter how far you go, but I'm going to want to label some of these surfaces later. So if I make it too small, it's going to be really hard to see those surfaces. So I'm going to go 1 meter. The body interaction actually doesn't matter because there's no other bodies. So I'm going to extrude 1 meter, and there I've done that. Just gotten out of the board 1 meter. Actually, while I'm at it, I'm going to label some surfaces that are going to be convenient if I do it now while it's still an airfoil, or this wing now. I'm going to label the trailing edge. I think I got that. So that line here is my trailing edge. I right-clicked, and I'm going to say rename. I'm going to call it trailing edge. That's just going to help me later when I'm creating my mesh. I'm going to want to refine around specific points, and if I have them labeled, I'm going to be able to refer to them. And then I'm going to try and get this leading edge here. It doesn't matter if it's exactly right. I just need to refine somewhere around here. That looks pretty good. I think it's probably, yeah, about there. It looks about right. Okay, I'm going to call this one my leading edge. Great. And then I'm going to return to a view that's just on my XY plane. Oops. Okay. Now, the next thing I need to do is to create the fluid domain. In 372, or in your undergraduate structures class, you most likely did an analysis where you use something like ANSYS or a finite element code. And in that case, you meshed the actual structure. Here, we're doing sort of the opposite. We want to mesh the domain around the structure. And so that creates an interesting challenge in that we don't have a natural boundary. How big is too big? You know, where do I go in terms of the volume? And what type of volume do I want to make? A good resource to help you with this is if you go to in the Steep portal or in the help menu for StarCCM, there's a best practices guide, and you can find this under simulating physics, and then guidelines for applying StarCCM, and then guidelines for dynamics. If you go there, it's divided between incompressible and compressible flows. In our case, we're doing incompressible. And so it recommends, as a best practice, to use a bullet-shaped far-field boundary with the domain that's around 8 to 10 body lengths or wingspans away from the body. So that's what we're going to do. We're going to create a bullet shape around. So to do that, you can see here we're on the XY plane. I'm going to create a sketch on the XY plane. I could use either of these two tools to create sort of that rounded nose. I'm going to use this one. Notice the order of points. And I'm going to click, and I don't really need to be precise here because I'm going to go in later and enter exact numerical values. I just need to sort of rough out the shape that I want. Okay, I've got that shape. Then I'm going to go to this line tool to create the back end of this bullet shape. These are going to be straight line, and then I'm going to close it off. Okay, this is sort of a classical domain, one of the classical domain shapes. Now I'm going to go in and actually give these precise numbers that I want. Just to make things easy, I'm going to keep this one right at the origin. And I defined a unit airfoil, so the chord length of this airfoil is 1. If you wanted to check, there's this little ruler tool and you can measure distances between things, but I already know that that's 1. So I'm going to, if I need to get it 10 body lengths away, I'm going to put y as 10. Okay. So better zoom out now. 10 body lengths away. This point here, I'm going to do the exact opposite. I'm going to put it at a minus 10. Okay, and then my far field, I want to make them line up, so this y should be 10. Actually, I'm just going to go a little further away just to make sure my wake, I have enough room for this wake. I'm going to go 15. And then same here, I'm going to go 15 and then minus 10. Okay, it's quite possible that I could squish in my boundaries a little bit, but the cell sizes toward my boundaries are going to be quite large. So I'm not going to save a lot of cells by trying to shrink that in too much, and I want to make sure that I'm not getting any boundary effects, so I'm going to be err on the side of generosity of my boundary here. Okay, so that's done. I need to take that same sketch and extrude it the same length as I did my airfoil, because I'm going to, let me just first extrude it and I'll talk about that in a minute. The idea here is that I need to create this flow field, and so I'm going to create the wing and I'm going to create the fluid domain, and then I'm going to subtract the wing volume from the fluid domain, and then what will be left is the fluid part that I actually want to simulate. I need to pick my body interaction to none. If I pick merge, since these two are completely overlapping, the one is going to get subsumed in the other, and I'll just only have this bullet shape. If I create none, then I'm going to have two separate bodies. So if we go under here in bodies, body 1 is my wing, body 2 here is the domain, and that's what I want, because then I can subtract one from the other. Just to make this a little easier for me, I'm going to rename this one airfoil, and I'm going to rename this one wing. Okay, and then I'm going to do a control click to select both of these, and then do Boolean subtract, and make sure that, oh, what did I name something wing? That's really weird. Yeah, sorry, I said domain, and then in my mind I guess I was thinking wing. Let's not confuse myself, and let's call this one the domain. Okay, I'm going to do a subtraction operation. So the target is what I want to subtract something from. So the domain is what I want to subtract from. The tool is what I'm going to subtract. So I'm going to take that airfoil volume and subtract it out of the domain. I hit OK. And what's happening? Is it still thinking? I don't think it did it, so what happened? I didn't get an error message either. So, no, it's just taking forever, sorry. I'm running this on a virtual machine, so it's a little bit slow. Okay, so what you see is I have my fluid domain, and now I've got this hole in the middle, which is exactly what I want. That hole is where the wing was, and oops. And the nice thing that happened is it transferred over those named edges, that leading edge and trailing edge. It transferred them over for me automatically because they were coincident. Otherwise, I'd have to try and name them now, and that's a little bit of a pain to get just the right view to see them on the inside. So now I can simulate the flow around the outside, and I'm not trying to simulate the flow going through the airfoil, so this is great. I'm going to name a few other faces just to make life easier. As we'll see, we can refer to these faces and edges later when we're creating a mesh and boundary conditions. So this is going to be my outlet boundary condition, so I'm going to rename this face as an outlet. Note you can see now why if I made my extrusion really small, it would be hard to grab these edges. And then the rest of these are going to be inlet. I'm still having a hard time grabbing that face. I'll grab this face. Then I'm holding down Control to select more than one. I don't want that. I want that face. And then on this side, this face. And then I'm right-clicking. I'm going to rename that the inlet. And then I'm going to grab the z=0 plane. That's going to be my actual domain in 2D, but it's here on the back side. Since I extruded in the positive z direction, I'm just going to call that z0. I guess I could call it domain, but it's going to get confused with my other domain. And I could name this face, but it's going to get flattened away when I go to 2D. If this was 3D, I'd want to rename that as well. Okay, I think I'm done with my geometry. I have everything I need. So I'm going to close 3D CAD. Okay, so I have a CAD model. The next thing I need to do is I need to create parts. So this is going to import them into my fluid domain. So I'm going to create a new geometry part. Just going to do that based on my solid body. I don't really need to change any of these defaults. And now I've got parts. And it's the domain, and it's also imported all my surfaces and the curves that I defined. Okay, so that's great. The next thing I need to do, specific for 2D, actually, so normally what I would do is I would create from these parts, I would create regions, and that's going to define these surfaces and the volumes that I need for boundary conditions. But before I do that, if I'm doing a 2D simulation, I need to let it know it's 2D. Otherwise, it's going to create a surface on both sides of that the z=0 and the z=1 domain, and I don't want that. So I'm going to do a badge for 2D meshing. It's just going to tell tell StarCCM this is going to be 2D, so I'm going to say this domain is going to be 2D, and I wanted to execute it after I'm done. And so it did that. Great. So now you can see it's got this little symbol next to domain, noting that it's been badged. I'm going to take this domain and assign parts to regions. Okay, and so I'm going to create one region for all parts. So I've only got one fluid volume region. That's all I need. It's going to create a boundary for each part. I actually want to create a boundary for each part's surface. That means I can create different boundary conditions on the different surfaces, which is normally what you will have. And everything else I'll keep, so I'll apply. And then I close. Okay, I'm going to need those later, but for now, my next step is to do a mesh. So I'm going to go to Operations and do a 2D mesh. It already knows it's 2D since I badged for 2D meshing. I'm going to mesh the domain. The recommended mesh is polygonal. That's the one we normally use. I'm going to see if it says something here in best practices. So both polyhedral and trim meshes have been proven successful. Talks a little bit about polyhedral mesh. They have an advantage of being smooth growth away from the body. So that's what we're going to use here. They're not polyhedral because this is 2D, so it's polygonal here. I am not doing a boundary layer. This is an Inviscid simulation, so I don't need a prism layer. So that's all I need. Okay, I've got my mesh. This is going to take a little bit of trial and error for you to get comfortable with doing these things. And even as you get comfortable, you're going to want to try and do things multiple times. So StarCCM uses something that's called a base size. You don't have to do this. You could do everything in terms of absolute size. But this can be convenient as you're doing mesh refinement studies that we talked about in class today. The idea of a base size is I'm going to pick some reference size. In this case, it's defaulted to 1 meter, but I can pick whatever I want. And every other mesh definition, I'm going to tie it back to that base size. And so then later, all I have to do is change this one number, make it bigger or smaller, and it's going to adjust everything else that was tied into it accordingly. There'll be some parameters I may not want to tie into it, especially as I get to viscous solutions, which we'll talk about in another day. But often I want to tie many things into a base size. I'm actually just going to keep my base size at 1 right now. That's the chord length. Some people like to make the base size a small fraction of the chord length. I'm just going to keep, a body length. I'm just going to keep it at 1. So that's just going to be a reference definition. Okay, target surface size. That's going to be near my surfaces. What is the target size of the mesh? And so you can change this. Notice it's relative to base, so it's going to be defined relative to whatever that base size is. You could make it absolute if you wanted to. I'm going to keep it relative. And so this relative size is now 100%. So this says I would want a mesh that was about the size of my airfoil, and that would be really not good. I'm going to say, let's say as just a starting point, I want about 100 mesh points around my around the airfoil. That's probably not enough, but let's just make that as a starting point. So that would be 1% of base, right? So 1% of base, and you can see here it's showing me what that is in absolute size. This is 0.01 meters. The minimum size, I probably want that to be maybe an order of magnitude smaller than that, because I'm going to want more refinement around the leading and trailing edge, maybe about 10 times as many more. So instead of 1%, this is going to be 0.1%. Again, those numbers all depend on what you picked for base size. They don't make sense without the base size, so they could be very different depending on what you chose. Curvature, this is saying how many points about do I want around a circle, how fast do we want to do a curvature. I'm going to do 72. That's about 1 every 5 degrees. I think that's probably a better resolution. Proximity, we generally don't need to change. The growth rate, we talked about this in class. I think 1.3 is a bit aggressive, so I'm going to change to 1.2. I think that's probably a good sort of upper limit, actually, about how fast to grow the cells. Okay, let's say that this is good. This is actually not good, but let's just see what it's going to look like. We're going to hit this mesh button here, or you could right-click here and execute it. And it's going to create my volume mesh, and you can see it's evaluating the quality of some of the faces. As we talked about in class, you want to make sure that things aren't too skewed, that their aspect ratio isn't really bad. And so it's trying to see if some of these are bad. It's going to redo the mesh. All these things that I've given it are, targets and minimums, and so it's not exactly specifying the mesh. There's a little bit of room to work with, and so it's just trying to find a mesh that meets the conditions that I've supplied as best as it can. Okay, so it's working on improving the quality here. While it's doing that, I don't think it's going to pop up a figure automatically, so here's how you do scenes. There's the geometry scene, which we can open up already because we have a geometry to see. It's being slow, partly because I'm running recording software and the virtual machine and the CFD at the same time, so sorry for the slowness. Meshing is almost done, and it looks like it completed. So there's the geometry. It's kind of boring, we've seen it already. I'm actually going to close that because I don't need to look at that. Let's look at the mesh. Okay, here's our mesh. Let's first look at, you should notice that it looks super wrong. We'll talk about why that is in a moment. But at the airfoil, as we zoom in, this is actually behaving kind of like what we thought, right? I picked this 1% to give maybe about 100 points around the airfoil, but allow it to get smaller in areas where it needs to. So it's trying to cover a little more cells around areas of high curvature. And then you can see it's growing as it goes out, right? And to me, I feel like this growth rate is actually still kind of aggressive. I might bring that down from 1.2, but it's growing and growing as we go out towards the boundary. But then what's happening here at the boundary, I've got a ton of cells at the boundary, and this is exactly what we do not need, right? There's no solid surfaces around the boundary. I don't want those there, but I haven't told my geometry anything else other than, get to a target surface size of 1% of the base. And so this is an edge, a boundary, and so it's going to do the same thing here. So we need to fix that, but first let's go look at the best practices here. It says away from the body, the mesh size can typically be large, right? About the order of the body length. So in our case, about a meter or 100% of our base size. So let's go back. The way we do that is we go to custom controls, and often we'll have multiple custom controls. So we're going to create a new one, and we're going to create it on the surface. I know it's not really a surface in 2D, but again, remember, in StarCCM, it's going to think of everything as sort of a 3D and then project it here on a 2D when it does. It'll actually solve it in 2D, but the nomenclature is still 3D. So I want to change this meshing around the inlet and outlet surfaces here. So now I've created a new surface control. I need to pick what parts that corresponds to, and I've created this inlet part and this outlet part, and those are the ones I'm going to apply it to. Okay, so that's good. And you can see it's sort of highlighted where that is. And around those surfaces, I want to override the defaults, right? So the target surface size right now, it says do the parent. I'm going to say no, I want you to do something custom. Don't take the parent one. And same with the minimum surface size. Take a custom. This curvature, growth rate, I think that's all probably okay. I don't need to do any wick refinement. We'll see what that is in a minute. For some reason, it always separates where you specify them, what you want, and where you specify the actual values, which I think is a little tedious, but that's how it is. Target surface size, 100% of base, that's what I want. I want it to be about the size of my wing chord. The minimum surface size, I actually don't want it to be any smaller than 100, so I'm going to say 100. My growth rate, I have it at 1.2, but I thought it was a little aggressive as I looked at it, so I'm going to change it down a little bit. If I go too small, right, I'm going to have too many cells, so I think this is probably going to be good. So let's rerun the mesh, see how this looks. You'll notice it ran a lot faster, right? The original one took a long time because it was trying to put a ton of cells around all this boundary here, but now that I don't have to do that, I have way fewer cells. I've got only 3,500 here, so not very many. We'll be, when we do 3D simulations, we'll often run things in the millions of cells. So this is a very small mesh by comparison. You'll notice here these cell sizes are about the size of my body, which is what I wanted. Out here, in the far field, things are not changing very much. In fact, they should hardly be changing at all. Otherwise, my domain boundaries are too small. And then you can see they're shrinking in. And as I go towards, I'm a little more happy with this growth rate. Things seem to be a little more gradual. I'm not getting too big of changes. And as a first cut, we'll definitely want to do some mesh refinement studies because this is probably not quite fine enough, but this looks as a reasonable place to start. Okay, so I'm pretty happy with this mesh, the starting point. But there are a few things that I want to do here, okay, just to show you. One is a wake refinement. In our case, we're doing an Inviscid simulation, so there is no wake. So actually a wake refinement is unnecessary, but I'm just going to show you how this can be done. The other is most of my changes are occurring at the leading and trailing edge, right? Because as we talked about with drag, it's much easier to resolve lift, especially when I'm doing CFD and I'm doing an integration of pressures. Most of my surface normals here, if I'm integrating along this top, upper, and bottom surface, are pointing upward, right? But if I look towards the leading edge and trailing edge, if I get the surface normal off just a little bit, that's going to affect my drag a lot. So I need to get a lot of cells around this leading and trailing edge so I get accurate drag values. So I'm going to add another custom control. I'm going to do it around a curve. Okay, and those curves are going to be my leading and trailing edge. Okay, great. So you can see those are being pointed out there. What do I want to do there? Well, I want to perhaps make a finer surface size. So I'm going to change the surface size to a custom, and then the minimum to a custom. The wake I don't want to do here because I've got the leading and trailing edge specified. And actually I said I was going to show you wake, but because this video is already getting long enough, I'm going to save that till we actually need it on viscous simulations. And if you're interested, the walkthrough that I linked in the homework actually shows you how to do that. Okay, so for the surface size, I want to make this pretty small. Let's say instead of 1%, let's go down to 0.1%, which was sort of my minimum size I specified before. I want that to be my target size here. And then a minimum size, I don't know, let's say 0.05%. Okay, and now let's see what that looks like. It's going to take a little bit longer, but it shouldn't take too long, and that's actually done. So you can see what it did is it created a lot more mesh cells around my leading and trailing edge, which is exactly what I wanted. I want to make sure that I'm getting fine enough resolution, because in the end, when StarCCM is evaluating lift and drag, it's going to do that by doing this integration pressures, and because the surface normal is changing so quickly, I need to get a fine resolution around those edges. So I think I'm pretty happy with this as a good starting point. Now what I can do, if I wanted to do mesh refinement studies, I'm not going to do it again because I want to keep this relatively short. If I go in and change this base size, I can now make this, well, let's just go ahead and do it. Let's just make this really big. This is not a good direction to go. This is the opposite of the way I want to go. But since everything was tied into the base size, you can see a lot of things changed. It actually didn't change too much, but you can see it made it a lot coarser here around the airfoil and around the airfoil because all of those things were tied into my base size. Okay, and so yeah, I'll take it back. It actually did change it quite a bit. So I'm going to go back to 1. And if I wanted to make it finer, I could go the other way, make my base size smaller. Again, this is just a convenient way to do, if I tie things in smartly, a convenient way to do a grid convergence study where I can change one number and get refinement in multiple areas. Okay, my mesh is done. Next step is I need to assign boundary conditions. So let's close off this mesh thing. Actually, I need to first specify the physics models that I'm going to use. So this is a continuous assumption. There are 2 ways I can do this. Actually, let me just right-click on physics here and select models. And again, if you go to best practices here, it's going to give you some guidelines here. We're not doing three-dimensional. We are doing steady. It says it suggests segregated flow for incompressible. For compressible flows, it actually suggests a coupled, but we're going to do segregated flow. We're doing constant density. We're not doing turbulent because ours is inviscid, and so we don't have RANs. But otherwise, the main thing we need to do here is to use this recommendation for segregated flow, which has better numerical behavior for this incompressible simulation. So this is a steady simulation, and you'll notice it will limit my choices depending on what I pick, so it's going to help guide me into things that are consistent. This is a gas. By the recommendation, I'm going to do a segregated flow. This is a constant density incompressible flow, and it's inviscid, and then I don't need any of these extra options, but there are things like if I wanted to add some gravity terms or radiation terms, so on, sort of specialized things. Okay, so close, physics models are set. I already defined my regions earlier. If I didn't do it before, I could go back to my domain and go and assign parts to regions. But now I've got things defined to regions. I've got the domain, let's see, it's calling it default, and I don't really like that name, so I'm going to call it airfoil, right? So let's give it a more useful name. Okay, well, I guess since I already defined my domains, it's not going to change that name. I could go and reassign it, but I'm not going to do that. So you can see it's associated with this airfoil. By default, it makes every surface a wall. So that's what I want for my airfoil, but I don't want my inlets and outlets to be walls. So I need to change those. This little symbol here is a wall, and you can also see here by type it says wall. Inlet, I'm going to choose, as we talked about in class, a velocity inlet for an incompressible flow. Notice it changed the symbol here. For the outlet, I'm going to make this a pressure outlet, again, as we talked about in class today. And you can see it's pointing out, yes, this is an outlet. So I've defined my boundary conditions, and now I need to define values for them. The pressure one is easy because I just want to keep it at atmospheric. And so that's going to be pressure 0. This is a gauge pressure, so it's relative to atmosphere. So I want to keep that at 0. So I'm done there. Velocity inlet, I need to give this a magnitude and a direction. So there are different ways you can specify it. I don't want to specify it normal to the boundary because that means it's going to be going in all sorts of different directions here for this bullet shape. That might be good for a different kind of shape, but that's not what I want here. I'm going to do in terms of components. Reference frame is a lab frame. You generally won't change that unless you're doing like a rotating simulation or you have multiple reference frames. And then the velocity, you can do it in terms of magnitude and direction or as components. Let's see, actually, I'm curious what that's going to look like if I change that to components. Yeah, actually, I think that's convenient. So I'm going to do that. Velocity, no, actually, no, I take that back. I like magnitude and direction because I need direction in a few other areas, as we'll see in a minute. So magnitude, I didn't really pick something to do, so I'm just going to make something up. 10 meters per second sounds good. Flow direction, let's say I want to do this at 5 degrees angle of attack. It is better, as you'll see, as should be obvious if we think about meshing, it's better if I want to change the angle of attack to just change my boundary condition. I just change the direction that it's coming in on the boundary. Otherwise, I'd have to change my airfoil geometry, rotate it, and then I'd have to do a remesh every time. That's going to be more complicated. It'd be better if I keep my mesh and just change the direction that the inflow is coming in. So I need to do 5 degrees. Let's see, I gotta figure out what that is, and I don't know what that is off the top of my head. So let's see, I'm just gonna pull up a little calculator here and see what is cosine of 5 degrees. I'm gonna write this number down because I'm gonna actually use it a couple times. If I was doing it really carefully, I might want to keep more significant fakes, but I'm just going to do 996. And then the sine is, again, just rough, 0.87. Okay, so I'm going to put those in as my direction. This is a unit vector here. So 0.996 and 0.087. The reason why I want to remember this is, one, if I had a wake, I generally, which we didn't do, if I had a wake mesh, I generally want to align that wake mesh more or less with my angle of attack or the free stream direction. The other is if I want to get forces like lift and drag, I kind of need to know what what these values are. Okay, so I've specified my boundary conditions. I put in a velocity, specified my pressure outlet. So everything is done here. You don't need to change anything here. These are be more specialized cases. So we're done with that. Now we move down to solvers. You're not going to change anything here. Again, this is a little more advanced if you want to change sort of some of the solution methods, criteria for stability, and so on. But we're going to leave those as defaults. Stopping criteria we will use for this first video. We're just going to keep the most simplest one, which is the default. How many steps we're going to run. I'm going to keep it at 1,000, but you can do more advanced things based on residuals or different fluid properties that you want to, or monitors that you want to look at. But let's just let it run for 1,000. And I'm almost ready to run. What I want to do is I want to create some reports. Okay, this is going to be useful for me to extract some information and also to monitor what's going on. So I've right-clicked here, and I'm going to do a new report. I guess I clicked too many times. And then you can see there are tons of stuff here, right, that I can look at. I'm just going to look at a force. And this first one, I'm going to call it drag. Again, this isn't really drag because I don't have any viscosity. This is just the pressure drag. And so this is a force. I could do a force coefficient, which actually would probably be nicer if I was monitoring things. Then I just need to go define the reference area. But to keep things simpler here in this shorter video, I'm going to just stick with a force. And now I got to say, what direction do I want that to be? That needs to be in my free stream direction. So I'm going to use these numbers that I'm remembering, 0.996 and 0.87. It's going to give me pressure and shear, but of course shear is 0, so really it's exactly the same as if I had just picked pressure. And this is in newtons. Okay, so this is my drag force. And then I'm going to create a second report. Here's force coefficient if you want to do those, which I'd probably recommend if you're doing something more meaningful and comparing to data. Okay, lift. So let's see, I just need to think a little bit about what this is. This is going to be the same kind of numbers, but just reversed a little bit. So in the x direction, it's going to be the smaller number with a negative, right, because it's tilted back. So minus 0.87, and then in the y, this vector is 0.996. Hopefully I did that right. Seems right to me. So that's going to be my lift. Okay, and then a convenient thing to do if you right-click these says create monitor and report, or sorry, and plot from report. So I'm going to do that, and I'm going to do that for lift too as well. So the monitor is just going to keep track of those data. It's going to output these to files and things that I can extract. Things that it's also going to track them in my residuals. And the plot is just going to create a plot of what's happening versus each iteration, so I can make sure that these are converging well. So as I run, I'm going to be looking at drag, lift. I'm also going to look at residuals, so I double-click that. We talked about that in class today. And because this is only 2D and it's only incompressible, I only have 3, right? Mass and then 2 directions of momentum conservation. Okay, I think I'm ready to run. So I'm going to click this run button. It looks like a person running. And it's starting to run, and getting a lot of reverse flow, which makes me think I messed up somewhere, which is definitely quite possible. And while I figure out if I messed up on something, I'm going to create a new scene to show you that as well. Okay, so I've got a geometry and a mesh scene. I can right-click here and go to new scene, or I can also go up here and create a scalar scene. These are very useful. We can visualize lots of different quantities. Let's say I want to, you right-click on this color bar, and there are lots of stuff I can visualize here. I'm going to look at just, first of all, just to sort of debug and make sure things are going okay. We look at velocity, magnitude, and you can see it's all over the place. I can that's becoming better. You can see it's quickly starting to stabilize, so this may have just been a transient. Okay, now we're starting to get a good solution. So you can see the velocity field looks pretty good. You can choose different ways to display this. I'm not going to get too much into post-processing here. Let's see. One, for example, is you can do what's called a smooth field. You might actually like to leave it like this because this shows me when you're doing meshing where my mesh boundaries are and if I actually have enough resolution. If it's too jagged like it is now, I may not have enough resolution, but when I finally want to create a plot, for publication, kind of smoothing some of those contours, make it look a little better. I don't like the rainbow color map because, well, you can read about the reasons why it distorts data in terms of representations. It's not a uniform, doesn't have uniform intensity. So another, I don't know if any of these really do, but this cool warm can be useful. This is actually better if you are looking at deviations around a mean, so it's not so great for velocity because this is what's called a diverging color map, so it should have a central thing around orange. Let's see if I have a continuous one. Maybe something like this tropical one. That looks pretty good. Okay, so here I can see my oh, sorry, we should have been looking at these monitors, right? Oh, and these are 0, and I can tell you why in a second. Residuals, you can see it took a while. They were starting to go down, and now they've started to level out. So that's good. Drag and lift are 0, which is amazing, but totally wrong. And the reason for that is I didn't pick any bodies. So I defined the direction, but there's no parts here. So for drag, I need to pick the airfoil, so it's going to do an integration around that surface, and then for lift, that surface as well. So you're not going to see their convergence. You would have seen them flatten out as well, but I just need to run even just for one more step and it'll give me them, but I'm going to run for a few more so you can see that they're flat. So this is going to jump up. And kind of flatten out and then lift. So if we've been watching them the whole time, you would have seen sort of a progression. Okay, and you can see numbers here. Residuals are looking good. Velocity is looking good. You can look at other things like pressure, although this is incompressible, so he's going to have a very close one-to-one relationship here. Okay, so you can see the suction peak toward the front and the stagnation here. We can look at these reports, extract values. We're not going to get into post-processing too much today. If there was a plot that you liked and you wanted to see it, you can right-click on them and export them, and it'll give you a CSV file that you can then go plot in your favorite programming language and do some post-processing on the data. We can also get raw values from these different quantities. And here's a report on lift. It's telling me what's coming from pressure and shear in all the different directions. Okay, so I think that's going to be enough for today. So besides my panicking that things weren't working well, which they were, actually, you know what, let's just make sure it wasn't a mesh issue. And by the way, this is actually a good technique. If you want to do mesh refinement, what will happen when I refine my mesh? Um, so I'm going to re-enable this and then remesh. So I'm going to get that better resolution towards the leading and trailing edge that I wanted. What's going to happen is, since I already have a solution, StarCCM is going to interpolate that solution onto this new mesh. So in other words, I'm going to be starting with a pretty good solution. The reason why my other one took a while is I started with a horrible solution, uniform flow everywhere, so it took a while to converge. But now that I'm starting with a really good solution, it's going to converge pretty quickly. And this can be a good technique to do mesh refinement. You can start with something pretty coarse, get sort of a rough solution, and then refine and run, refine and run. And that could actually be faster oftentimes than starting with a really fine mesh and running, just because, that finest mesh is just going to take a long time to run. So if you can get it warm started with something better, that can be more effective. So let's change my maximum steps here. Oops. Let's go to 7,000. Run. And you should see a discrete jump in the residuals, because now a bunch of them have errors because I created a bunch of small cells that weren't there before, so they had high error. Don't worry too much about this magnitude here. You want to see this flattening out. I'm not sure if these are normalized. I'd have to look into that, because that doesn't really make sense as a number. So they're still working, and then lift, you can see I changed. So I'm actually getting more accurate values here. So this is an indication that my original mesh wasn't good enough. If it was, I should have got the same answer, right? And you can see it's not the same. I'm getting a little bit higher lift, and my drag actually, you can see, was way different. And this is indicative of what we talked about, that getting the lift is actually pretty easy without too good of a mesh. So we went from 49 to 50. That's maybe like 2%, 1 to 2% error here. I can't quite tell exactly what those numbers are. Whereas my drag, I was off by like a factor of 2. So that's a lot. And so, doing these mesh refinement studies is really important to make sure you have a good enough mesh. Okay, so yeah, everything is now behaving happily. So I think that's it for today.